The wave equation is an important second-order linear partial differential equation for the description of waves as they occur in physics, such as sound waves, light waves, and water waves. It arises in fields like acoustics, electromagnetics, and fluid dynamics. Historically, the problem of a vibrating string such as that of a musical instrument was studied by Jean-Léon d'Alembert, Leonhard Euler, Daniel Bernoulli, and Joseph-Louis Lagrange. In 1746, Alembert discovered the one-dimensional wave equation, and within 10 years Euler discovered the three-dimensional wave equation. Introduction. The wave equation is a hyperbolic partial differential equation. It typically concerns a time variable t, one or more spatial variables x1, x2, xn, and a scalar function u equals u, x1, x2, xn, t, whose values could model the displacement of a wave. The wave equation for u is where 2 is the spatial Laplacian, and where c is a fixed constant. Solutions of this equation, that are initially zero outside some restricted region, propagate out from the region at a fixed speed, in all spatial directions, as do physical waves from a localized disturbance. The constant c is identified with the propagation speed of the wave. This equation is linear, as the sum of any two solutions is again a solution. In physics, this property is called the superposition principle. The equation alone does not specify a solution. A unique solution is usually obtained by setting a problem with further conditions, such as initial conditions, which prescribe the value and velocity of the wave. Another important class of problems specifies boundary conditions, for which the solutions represent standing waves, or harmonics, analogous to the harmonics of musical instruments. The wave equation, and also modifications of it, are found in elastic physics, quantum mechanics, plasma physics, and general relativity. For example, scalar wave equation in one space dimension. French scientist Jean-Baptiste Léonhard d'Alembert, b. 1717, discovered the wave equation in one space dimension. The wave equation in one space dimension can be written like this. This equation is typically described as having only one space dimension x, because the only other independent variable is the time t. Nevertheless, the dependent variable y may represent a second space dimension, as in the case of a string that is located in the xy plane. Derivation of the wave equation. The wave equation in one space dimension can be derived in a variety of different physical settings. Most famously, it can be derived for the case of a string that is vibrating in a two-dimensional plane, with each of its elements being pulled in opposite directions by the force of tension. Another physical setting for derivation of the wave equation in one space dimension utilizes Hooke's law. In the theory of elasticity, Hooke's law is an approximation for certain materials, stating that the amount by which a material body is deformed, the strain, is linearly related to the force causing the deformation, the stress. From Hooke's law, the wave equation in the one-dimensional case can be derived from Hooke's law in the following way. Imagine an array of little weights of mass m interconnected with massless springs of length h. The springs have a spring constant of k. Here the dependent variable u, x, measures the distance from the equilibrium of the mass situated at x, so that u, x, essentially measures the magnitude of a disturbance, i.e. stress, that is traveling in an elastic material. The force is exerted on the mass m at the location x plus hr. The equation of motion for the weight at the location x plus h is given by equating these two forces, where the time dependence of u, x, has been made explicit. If the array of weights consists of n weights spaced evenly over the length L equals nh of total mass m equals nm, and the total spring constant of the array k equals k/n, we can write the above equation as taking the limit n, h0, and assuming smoothness, one gets KL2/m is the square of the propagation speed in this particular case. 1D standing wave as a superposition of two waves traveling in opposite directions. General solution. Algebraic approach. The one-dimensional wave equation is unusual for a partial differential equation, in that a relatively simple general solution may be found. Defining new variables changes the wave equation into, which leads to the general solution, or equivalently. In other words, solutions of the 1D wave equation are sums of a right-traveling function f and a left-traveling function g. Traveling means that the shape of these individual arbitrary functions with respect to x stays constant, however the functions are translated left and right with time at the speed c. This was derived by Jean-Léon d'Alembert. Another way to arrive at this result is to note that the wave equation may be factored, and therefore these last two equations are vection equations, one left-traveling and one right, both with constant speed c. For an initial value problem, the arbitrary functions f and g can be determined to satisfy initial conditions. The result is Alembert's formula. In the classical sense, if f, x, ck, and g, x, ck1 then u, t, x, ck. However, the waveforms f and g may also be generalized functions, such as the delta function. In that case, the solution may be interpreted as an impulse that travels to the right or the left. The basic wave equation is a linear differential equation, and so it will adhere to the superposition principle. This means that the net displacement caused by two or more waves is the sum of the displacements which would have been caused by each wave individually. In addition, the behavior of a wave can be analyzed by breaking up the wave into components, e.g. the Fourier transform breaks up a wave into sinusoidal components. Plane wave eigenmodes. Another way to solve for the solutions to the one-dimensional wave equation is to first analyze its frequency eigenmodes. A so-called eigenmode is a solution that oscillates in time with a well-defined angular frequency, with which the temporal part of the wave function for such eigenmode takes a specific form. The rest of the wave function is only dependent on the spatial variable, hence amounting to separation of variables. Now writing the wave function as, we can obtain an ordinary differential equation for the spatial part, which is precisely an eigenvalue equation for, hence the name eigenmode. It has the well-known plane wave solutions with wave number. The total wave function for this eigenmode is then a linear combination, where complex numbers depend in general on any initial and boundary conditions of the problem. Eigenmodes are useful in constructing the full solution to the wave equation, because each of them evolves in time trivially with a phase factor. So with this, the full solution can always be decomposed into an eigenmode expansion, or in terms of the plane waves, which is exactly in the same form as in the algebraic approach. Functions are known as the Fourier component, and are determined by initial and boundary conditions. This is a so-called frequency domain method, alternative to direct time domain propagations, such as FDTD method of the wave packet. Scalar wave equation in three space dimensions. Swiss mathematician and physicist Leonhard Euler, b. 1707, discovered the wave equation in three space dimensions. The solution of the initial value problem for the wave equation in three space dimensions can be obtained from the solution for a spherical wave. This result can then be used to obtain the solution in two space dimensions. Spherical waves. The wave equation is not invariant under rotations of the spatial coordinates, because the Laplacian operator is not invariant under rotation. However, similar to Schrödinger's equation in three dimensions, one can solve for the solution with zero orbital angular momentum, in which case the Laplacian operator reduces to a rotationally invariant form. Therefore one may expect to find solutions that depend only on the radial distance, but not angle variables, from a given point. Such solutions then satisfy. This equation may be rewritten as, where the quantity Ru, T, satisfies the one-dimensional wave equation. Therefore there are solutions in the form, where f and g are general solutions to the one-dimensional wave equation, and can be interpreted as respectively an outgoing or incoming spherical wave. Such waves are generated by a point source, and they make possible sharp signals, whose form is altered only by a decrease in amplitude as r increases. See an illustration of a spherical wave on the top right. Such waves exist only in cases of space with odd dimensions. For physical examples of non-spherical wave solutions to the 3D wave equation that do possess angular dependence, see dipole radiation. Monochromatic spherical wave. Cutaway of spherical wave fronts, with a wavelength of 10 units, propagating from a point source. Although the word monochromatic is not exactly accurate since it refers to light, or electromagnetic radiation with well-defined frequency, the spirit is to discover the eigenmode of the wave equation in 3 dimensions. Following the derivation in the previous section on plane wave eigenmode, if we again restrict our solutions to spherical waves that oscillate in time with well-defined angular frequency, then the transformed function has simply plane wave solutions. Or, from this we can observe that the peak intensity of the spherical wave oscillation, characterized as the squared wave amplitude, drops at the rate proportional to an example of the inverse square law, solution of a general initial value problem. The wave equation is linear in U, and it is left unaltered by translations in space and time. Therefore we can generate a great variety of solutions by translating and summing spherical waves. Let be an arbitrary function of 3 independent variables, and let the spherical waveform f be a delta function, that is, let f be a weak limit of continuous functions whose integral is unity, but whose support, the region where the function is non-zero, shrinks to the origin. Let a family of spherical waves have center at, and let r be the radial distance from that point. Thus, if U is a superposition of such waves with weighting function, then the denominator for C is a convenience. From the definition of the delta function, you may also be written as where and are coordinates on the unit sphere S, and is the area element on S. This result has the interpretation that U, T, X, is T times the mean value of on a sphere of radius CT centered at X. It follows that the mean value is an even function of T, and hence if. Then these formulas provide the solution for the initial value problem for the wave equation. They show that the solution at a given point P, given T, X, Y, Z, depends only on the data on the sphere of radius CT, that is intersected by the light cone drawn backwards from P. It does not depend upon data on the interior of the sphere. Thus the interior of the sphere is a lacuna for the solution. This phenomenon is called Hugon's principle. It is true for odd numbers of space dimension, where for one dimension the integration is performed over the boundary of an interval with respect to the Dirac measure. It is not satisfied in even space dimensions. The phenomenon of lacunas has been extensively investigated in Atiyah, Bott, and Garding. 1970-1973. Scalar wave equation in 2 space dimensions. In 2 space dimensions, the wave equation is. We can use the 3-dimensional theory to solve this problem if we regard U as a function in 3 dimensions that is independent of the 3rd dimension. If, then the 3-dimensional solution formula becomes where and are the first 2 coordinates on the unit sphere, and D is the area element on the sphere. This integral may be rewritten as an integral over the disk D with center X, Y, and radius CT. It is apparent that the solution at T, X, Y depends not only on the data on the light cone, where, but also on data that are interior to that cone. Scalar wave equation in general dimension and Kirchhoff's formulae. We want to find solutions to at U equals 0 for U, Rn, 0. R with U, X, 0, equals G, X, and up, X, 0, equals H, X, see Evans, for more details. Odd dimensions. Assume N3 is an odd integer and GCM, plus 1, Rn, HCM, Rn, for M equals N, plus 1/2. Let and let. Then UC2, Rn 0, at U equals 0 in Rn, 0. Even dimensions. Assume n2 is an even integer and GCM plus 1, Rn, HCM, Rn, for m equals n plus 2/2. Let. Then UC2, Rn 0, U equals 0 and Rn 0. Problems with boundaries. 1. Space dimension. The Sturm-Liouville formulation. A flexible string that is stretched between 2 points x equals 0 and x equals L satisfies the wave equation for t greater than 0 and 0xL on the boundary points. You may satisfy a variety of boundary conditions. A general form that is appropriate for applications is where a and b are non-negative. The case where u is required to vanish at an endpoint is the limit of this condition, when the respective a or b approaches infinity. The method of separation of variables consists in looking for solutions of this problem in the special form. A consequence is that the eigenvalue must be determined so that there is a non-trivial solution of the boundary value problem. This is a special case of the general problem of Sturm-Liouville theory. If a and b are positive, the eigenvalues are all positive, and the solutions are trigonometric functions. A solution that satisfies square integrable initial conditions for u and a can be obtained from expansion of these functions in the appropriate trigonometric series. Investigation by numerical methods. Approximating the continuous string with a finite number of equidistant mass points, one gets the following physical model. Figure 1. 3 consecutive mass points of the discrete model for a string. If each mass point has the mass m, the tension of the string is F, the separation between the mass points is x and I equals 1, and are the offset of these endpoints from their equilibrium points, i.e. their position on a straight line between the two attachment points of the string. The vertical component of the force towards point I plus 1 is 1. And the vertical component of the force towards point I1 is 2. Taking the sum of these two forces, and dividing with the mass m1 gets for the vertical motion, 3. As the mass density is. This can be written, for the wave equation is obtained by letting x0, in which case ui, t, takes the form u, x, t, where u, x, t, is continuous function of two variables, takes the form, and but the discrete formulation, 3, of the equation of state with a finite number of mass point is just the suitable one for a numerical propagation of the string motion. The boundary condition, where L is the length of the string, takes in the discrete formulation the form that for the outermost point u1, and in the equation of motion are 5 and 6, while for 1 in 7, where if the string is approximated with 100 discrete mass points, one gets the 100 coupled second-order differential equations, 5, 6, and 7, or equivalently 200 coupled first-order differential equations. Propagating these up to the times. Using an 8th-order multi-step method, the 6 states displayed in Figure 2 are found. Figure 2, the string at 6 consecutive epochs, the first, red, corresponding to the initial time with the string in rest. Figure 3, the string at 6 consecutive epochs. Figure 4, the string at 6 consecutive epochs. Figure 5, the string at 6 consecutive epochs. Figure 6, the string at 6 consecutive epochs. Figure 7, the string at 6 consecutive epochs. The red curve is the initial state at time 0 at which the string is let free in a predefined shape with all. The blue curve is the state at time, i.e., after a time that corresponds to the time a wave that is moving with the nominal wave velocity would need for 1/4 of the length of the string. Figure 3 displays the shape of the string at the times. The wave travels in direction right, with the speed without being actively constrained by the boundary conditions at the two extremes of the string. The shape of the wave is constant, i.e. the curve is indeed of the form f, x, c, t. Figure 4 displays the shape of the string at the times. The constraint on the right extreme starts to interfere with the motion, preventing the wave to raise the end of the string. Figure 5 displays the shape of the string at the times when the direction of motion is reversed. The red, green and blue curves are the states at the times, while the three black curves correspond to the states at times with the wave starting to move back towards left. Figure 6 and Figure 7 finally display the shape of the string at the times, and the wave now travels towards left and the constraints at the endpoints are not active anymore. When finally the other extreme of the string, the direction will again be reversed in a way similar to what is displayed in Figure 6. Several space dimensions. A solution of the wave equation in 2 dimensions, with a zero displacement boundary condition, along the entire outer edge. The one-dimensional initial boundary value theory may be extended to an arbitrary number of space dimensions. Consider a domain D in m-dimensional X space, with boundary B. Then the wave equation is to be satisfied if X is in D and T greater than 0. On the boundary of D, the solution U shall satisfy, where n is the unit outward normal to B, and is a non-negative function defined on B. The case where U vanishes on B is a limiting case for approaching infinity. The initial conditions are where f and g are defined in D. This problem may be solved by expanding f and g in the eigenfunctions of the Laplacian in D, which satisfy the boundary conditions. Thus the eigenfunction v satisfies in D, and on B. In the case of 2 space dimensions, the eigenfunctions may be interpreted as the modes of vibration of a drumhead stretched over the boundary B. If B is a circle, then these eigenfunctions have an angular component, that is a trigonometric function of the polar angle, multiplied by a Bessel function of integer order of the radial component. Further details are in Helmholtz equation. If the boundary is a sphere in 3 space dimensions, the angular components of the eigenfunctions are spherical harmonics, and the radial components are Bessel functions of half-integer order. Inhomogeneous wave equation in 1 dimension. The inhomogeneous wave equation in 1 dimension is the following. With initial conditions given by the function s, x, t, is often called the source function, because in practice it describes the effects of the sources of waves on the medium carrying them. Physical examples of source functions include the force driving a wave on a string, or the charge or current density in the Lorentz gauge of electromagnetism. One method to solve the initial value problem with the initial values, as posed above, is to take advantage of a special property of the wave equation in an odd number of space dimensions, namely that its solutions respect causality. That is, for any point, xi, t, the value of u, xi, t, depends only on the values of f, xi, plus cti, and f, xi cti, and the values of the function g, x, between xi cti and xi plus cti. This can be seen in Allembert's formula, stated above, where these quantities are the only ones that show up in it. Physically, if the maximum propagation speed is c, then no part of the wave that can propagate to a given point by a given time can affect the amplitude at the same point and time. In terms of finding a solution, this causality property means that for any given point on the line being considered, the only area that needs to be considered is the area encompassing all the points that could causally affect the point being considered. Denote the area that casually affects point xi, t, as or c. Suppose we integrate the inhomogeneous wave equation over this region. To simplify this greatly, we can use Green's theorem to simplify the left side to get the following. The left side is now the sum of 3 line integrals along the bounds of the causality region. These turn out to be fairly easy to compute. In the above, the term to be integrated with respect to time disappears because the time interval involved is 0, thus dt equals 0. For the other 2 sides of the region, it is worth noting that xct is a constant, namely xi cti, where the sign is chosen appropriately. Using this, we can get the relation dx dt equals 0, again choosing the right sign. And similarly for the final boundary segment. Adding the 3 results together and putting them back in the original integral. Solving for u, xi, t, we arrive at In the last equation of the sequence, the bounds of the integral over the source function have been made explicit. Looking at this solution, which is valid for all choices, xi, t, compatible with the wave equation, it is clear that the first two terms are simply Albert's formula, as stated above, as the solution of the homogeneous wave equation in one dimension. The difference is in the third term, the integral over the source. Other coordinate systems. In 3 dimensions, the wave equation, when written in elliptic cylindrical coordinates, may be solved by separation of variables, leading to the Mathieu differential equation. Further generalizations. 2 model dispersive wave phenomena, those in which the speed of wave propagation varies with the frequency of the wave. The constant c is replaced by the phase velocity. The elastic wave equation in 3 dimensions describes the propagation of waves in an isotropic homogeneous elastic medium. Most solid materials are elastic, so this equation describes such phenomena as seismic waves in the Earth and ultrasonic waves used to detect flaws in materials. While linear, this equation has a more complex form than the equations given above, as it must account for both longitudinal and transverse motion. Where and are the so-called lame parameters describing the elastic properties of the medium? Is the density. F is the source function, driving force. And U is the displacement vector,